All right, so here we go. For problem number one, everything here is given in grams. And in order to do empirical formulas, we just want to convert it all to some form of moles. So instead of being in grams, we want to convert it down to moles. So if I got 36 grams of carbon, and we know its carbon is 12 grams per mole, that means that I got 3 moles, right? And then hydrogen, it's 6. And once again, for hydrogen, it's not H2, it's just one hydrogen, so therefore it's just one. And so that means I got 6 moles of hydrogen and 24 grams of oxygen. If I divide that by 16, which is the molar mass of oxygen, would give me 1.5. And now in order to get a ratio, we need to divide them all by the smallest. So here we're going to divide everything by the 1.5. And now we can get our empirical formula. So now we see our empirical formula would be C2H4. And there we go. That's it for that one. Now this one's already given us into moles. So it says it's 0.75 moles of K, 0.75 moles of Cr, 2.6 moles. So if I got 0.75, 0.75, and 2.6 respectively, K, right, this is K, Cr, and O. So divide them all by 0.75. And obviously it's 1, 1, and 2.6 divided by 0.75. So that gives me approximately 3.5, but I can't have, so we can't have this decimal. So we just need to multiply everything by 2 to give me to whole numbers. So that means it's going to be K2Cr2O7. And that kind of looks right because that would be our chromate atom. And so there we go with that one. All right, so next problem, it says explain why the sample was heated 3 times. So we're taking this, so Na2SO4, and then the N just means some moles of water. So why do we have to heat it 3 times? Because we want to get it to constant mass. Because what does constant mass mean? Constant mass means that there's no more water being driven off. So here there's very little change. So here there's very, very little change in the mass. So we can conclude that there's no more water because there's virtually no change in the mass after we're continuing to heat it. So determine the mass of the sample before heating. So we're just going to look at a couple. So there we just have to look at the mass of the sample before the initial mass, and then subtract the container. Then the water, we're going to take that difference, so we can see what it is when we got down to this. So what we really want to do is just figure out what is it when it's dry. So taking our last value minus the container, that gives me 1.593 grams of sample. Then we can subtract that out of what was the mass. So therefore the difference between those two must have been the water. So the 3.16 minus the 1.593 must have been the water, or 2.019 grams of water. Well, now I know if I have 2.019 grams of water, we can determine the mass of water. Well, the moles of water, so divide that by 18 would give me my moles. All right, and we'd already figured out the mass of the anhydrite, which was the dry sample, was 1.593 grams, because that's what we'd figured out earlier. That was our dry sample. And then, so now I can figure out the moles of the anhydrite. So that's just going to be sodium sulfate. So I know sodium is mass of 23, so 23 and 2 would be 46. And sulfur is 32, and oxygen 16 times 4 is 64. So if I add all that up, all right, so now we know the moles of the water, and we know the moles of the anhydrite, and so we can just do a ratio to figure out what's that ratio. So if I take the 0.1122 divided by the 0.0112, and that's going to give me approximately, so that'd give me approximately 10 moles of water. So I know then that's going to be Na2SO4 and then dot, and then that's where we get our moles, or 10 moles of water. And so that's how we write that hydrated compound. All right, so for the next one, looks like we have a 1.74 gram sample. I have so calcium sulfate with 2 moles of water. We want to know what percent of the hydrate is water. Well, I know if I got 2 moles of water, and we know that water is 18 grams per mole, that means I'm going to have 36 grams of water as compared to 1.745. So what is that percent? All right, now we just need to figure out what is the mass or the grams of calcium sulfate. So now we know the molar mass of calcium sulfate. So calcium 40, sulfur 32, oxygen, there are 4 of them, so it'd be 64. That makes 136. So therefore, the total mass of the whole compound, 36 and 136, makes 172. So I can take what is the water out of the 172 total and give me a percent, which would give me 20.9% water out of the compound. It says how many grams of water are present. Well, then I can take that and do it that way. So out of the 1.745 total grams, we know that 20% of it is water. All right, so therefore 0.365 grams of the 1.74 grams is water. Now we're going to place this sample in a crucible. So the original sample in a crucible, which is basically a little porcelain cup, so that way you could heat it up, or it could be brass or steel. That way we can heat it up to constant mass. It says what would be the mass of the crucible and the anhydrite, meaning it's dry. So therefore we're going to take our 1.745 and obviously subtract it from, because we've removed all the water. And then we're going to add the mass of the crucible to that. And that would give me the total mass of the sample and the crucible, what we should expect. All right, so here we're putting brass and 35.123 grams of hydrochloric acid together. We're going to get some hydrogen gas, obviously, therefore that's going to escape. So we're going to get some loss of the mass. So it says the remaining sample is this. Well, we know the original sample, so our original sample would have been the 1.203 plus the 35.123, and the remaining sample, 36.309, would have been log, right? So that's what's remained. So we take our original sample minus whatever we had left, and therefore that would give us the hydrogen gas that escaped. Therefore, the mass of the hydrogen gas must have been 0.017 grams. The mass of the zinc reacted. So now we can figure out that moles. So we can go from, basically we're going to go from grams to grams. So using our stoichiometric relationships. So a little stoichiometry here. We're going to go from grams of hydrogen to grams of zinc. So we know the hydrogen. So if I divide that by 2, give us our moles. So now we can just do a little stoichiometry. So I know if it's moles of zinc, moles of hydrogen, we got to go to moles of zinc, and obviously that's a 1-to-1 ratio. So 1 hydrogen for 1 zinc. So 1 hydrogen for every 1 zinc. And now just multiply by the mass of zinc, 65.38 grams for every 1 mole of zinc. And that gives me 0.556 grams of zinc that reacted. It says what was the percentage of zinc by mass in the alloy? Well, only in this case, only the zinc is reacting, not the copper, but we have a 1.23, right? So it was 0.556 grams of zinc that reacted out of the total sample, 1.203. So therefore I can get a percentage. All right, so for this next question here, right, we see that sodium bromide, so we have NaBr that has a 22.3% mass of total mass. So if I'm going to change it from bromine to chlorine, well, we know chlorine is lighter than bromine. Chlorine is a much lighter than bromine. So our total is going to decrease. So when we're doing our percentages, we know it's the mass of whatever our element is divided by the total mass. So if our total decreases, and then therefore chlorine is lower than bromine, we know we're going to get an increase in the percentage of sodium because of that difference in the total mass. Vice versa, if we're going to use iodine instead of bromine, iodine would be much higher mass than bromine, so our total is going to increase, and therefore we're going to get a percent decrease in the percentage of sodium. Now these, I'm assuming you guys can all do these pretty easily. I'm just going to do the shortcuts for a couple of them. So we know, looking at zinc, so zinc would be, all right, so zinc is in the fourth period, right? So I know that's going to be then argon, and then 4s2 3d10. If I'm going to take 2 away from zinc, well, anytime we do a +2, we know we're taking 2 away. So the question is what 2 are you taking away? Well, we always know when we remove electrons, we remove them from the highest energy orbital. So instead of, that would be the 4th energy orbital. So the 4s2 would go away, and we'd be left with the 3d10. Vice versa, so and I'm only going to do this couple. So phosphorus, I know, is element 15, and it's in the 3rd column. So that would be then neon. Actually, let's do phosphorus first. All right, so if I was going to do, oops, oh well. If I was going to do phosphorus, it would be neon, and then 3s2, 3p3. Right? And then here we know negative means we're adding, so that's going to be neon 3s2, adding 3 to the outside energy, so 3p6. Right? And then magnesium +2, so I know +2 means we're removing 2, so instead of it being 3s2, this is going to remove those 2 outside 3s2s, and so forth and so on. Right? Here, iron, we got iron +2, iron +3. So we know iron is normally argon, and then 4s2, 3d6. If it's +2, we know we're removing 2 electrons. The question is what 2 are we going to remove? And so we wouldn't remove just the 4s2 and leave the 3d6, because remember what happens is that it's less energy when it's half full, so it's going to be 4s1, 3d5, leaving the s orbital half full and the d orbital half full, because then remember, if we're looking at half full orbitals, we only have 1 electron in that, instead of it being that electron pair repulsion, so there's no electron pair repulsion, and therefore lower energy orbital. And same way here, this is going to now remove that extra, which one? The outside energy orbital. So it's going to remove the 4s1 and just leave the 3d5, which is why those transition metals can form multiples, because of that, pulling from both d and s orbitals. All right, so looking at Coulomb's law. So Coulomb's law is force. We have some kind of constant, and that's where we're looking at a charge. So that's charge over distance squared. So Q is the charge, and R is the radius, or the radius of the atom, or the distance between them. So does the force of attraction repulsion increase, decrease, or remain the same when the distance between the charges increases? So if that distance between the 2 charges, so if the distance increases, so if R goes up, our denominator goes up, what must happen to the force? The force must decrease. So here, if the radius increases, the force must decrease. Right? So if the same thing here, if the radius is decreasing, our denominator is getting smaller. A smaller denominator means an increase in the force or the attraction between them. If the charge increases, so if our numerator increases, so if Q goes up, then the force must go up. And then the same way, if the magnitude of the charge, now when we're thinking about charge, we're talking about +1 versus +2 versus +3. So the magnitude of the charge, or -1, -2, -3, so forth and so on. So when we're looking at the charges, a +2 would have a greater attraction than a +1, and vice versa, +3 would have a greater attraction than any of them. If the charge decreases, then obviously if charge is going to decrease, then our force is also going to decrease. All right, and here we know copper and chromium. So when we're thinking about copper, chromium, copper we would normally expect to be 4s2 3d9, but remember it doesn't do that. Why? Because it is less energy. So when we make it 4s1, oh, not 4, when we make it 4s1 3d10, because we have less electron pair repulsions and therefore more stable, right, more stable configurations. So less electron pair repulsions means we're going to have less charge, right? So that's going to make it more stable, and therefore that's what creates those exceptions. Same way for chromium, instead of being 4s2 3d4, it becomes 4s1 3d5, making those less electron pair repulsions, right? Because once again, if I got an S and a D, we know the D would be like this. So I only have one in each, and therefore there's no repulsions in each electron orbital. So because there's no repulsions, we have a lower energy, more stable configuration.